Let's jump right into this explainer and uncover the invisible math that ChatGPT literally uses millions of times a second just to understand exactly what your sentences mean. I mean, think about it. Every single time you hit enter, this massive calculation happens behind the scenes, instantly transforming your words into a language a machine can actually comprehend.
You'll see every sentence you type gets converted into a vector, a literal arrow floating in mathematical space. But here's the million-dollar question. How do we actually calculate if two of these conceptual arrows are similar? That single question is basically the backbone of search engines, recommendation systems, and honestly, every chatbot you've ever used. Think about this comparison for a second. Somehow, the AI knows that sentence A, I love machine learning, points in a completely different conceptual direction than sentence C, I ordered pizza. To the AI, these aren't English sentences anymore, right? They're just pure numeric coordinates. So, here is our roadmap to solving this conceptual mystery. First, we'll look at the AI similarity problem, followed by the magnitude trap. Then we'll get into deriving cosine similarity, run through a worked numerical example, explore real-world AI applications, and finally, do a summary connecting all the math.
Okay, Section 1, the AI similarity problem, combining dot products and norms.
We've got two fundamental mathematical puzzle pieces that we really need to combine to solve our similarity problem. We absolutely need the dot product, which measures how much our vectors agree in direction, and we need vector norms, which measure their actual length. When we merge these two concepts together, bam, they form our master formula for similarity.
Let's move to Section 2, the magnitude trap, why distance isn't enough.
Now, a lot of people just starting out assume we should just measure the physical distance between 2 points. I mean, closer points should mean more similar ideas, right? Well, actually, no. That is a massive mathematical trap. Notice what happens with these coordinates. Vector A is at 1, 1, and vector B is way out at 10, 10. They are pointing in the exact same direction. If A is I love AI, B is just a way more intense I really love AI. But their physical Euclidean distance is nearly 13 units apart. If we go by raw distance, they look completely unrelated. Crazy, right?
So the absolutely crucial takeaway here is that measuring raw distance is entirely misleading. Why? Because distance relies heavily on magnitude, how long the vector actually is. But AI, especially when dealing with embeddings, needs to focus purely on direction. We want to know what idea the vector is pointing toward, not necessarily how loud it's shouting that idea.
All right, Section 3, deriving cosine similarity, measuring angles. So if magnitude is throwing us off, we need a mathematical tool to just strip it away completely and measure the pure angle between the vectors. Intuitively, 0 degrees means maximum similarity. They overlap perfectly. 90 degrees means they're perpendicular, so totally unrelated with 0 shared direction, and 180 degrees, that means they're exact opposites. Now we just need a way to calculate this programmatically.
Let's walk through the derivations step by step. We start with a classic geometry formula you might remember. The dot product of A and B equals the product of their magnitudes multiplied by the cosine of the angle between them. But remember, we don't want that raw dot product because magnitude is still polluting it. So what do? We divide both sides by the product of the magnitudes. By doing that, we perfectly isolate the cosine of the angle. It's so elegant.
And this elegant math gives us a really clean, bounded similarity score. Because we isolated cosine, our score will literally always fall exactly between -1 and +1, no matter how long the original arrows were. +1 means identical direction, 0 means absolutely no relationship, and -1 means exactly opposite.
Up next is Section 4, a worked numerical example, putting the math into practice.
Let's say we have vector A at 1, 2, 3, and vector B at 4, 5, 6. If we follow our 3 steps, we first calculate the dot product by multiplying the corresponding components and adding them all up to get 32. Next, we find the individual norms, the lengths, which come out to roughly 3.74 and 8.77. Finally, we divide our dot product of 32 by those multiplied norms, and we get 0.974. That number is incredibly close to 1, which proves mathematically that these two vectors point in almost the exact same direction.
On the flip side, if we test perfectly perpendicular vectors resting right on our axes, like A at 1, 0 and B at 0, 1, the dot product calculation is simply 1 times 0 plus 0 times 1. It just equals 0. Mathematically, this instantly confirms that they share absolutely zero directional relationship. The angle really doesn't lie.
Moving on to Section 5, real-world AI applications, how AI uses embeddings. Now, the really crucial point here is understanding how this one isolated equation actually powers the entire modern AI landscape. This precise math is the literal backbone behind judging if sentences mean the same thing in semantic search. It's exactly how RAG systems, Retrieval-Augmented Generation, can accurately retrieve documents from a knowledge base to answer your prompts. It's the core logic querying massive vector databases like Pinecone, and yeah, it's even how Netflix and Spotify recommend your next favorite show or song.
Now here is a really fascinating engineering shortcut. If developers normalize their vectors beforehand, which basically means they forcefully scale them to have a length of exactly 1, the norms at the bottom of our equation just become 1 times 1. This means that whole complex formula effortlessly simplifies to just a raw dot product calculation. That saves a massive amount of compute time.
And the best part is just how accessible this is to actually program. Whether you code every algebraic set from scratch to truly understand the mechanics, or you use built-in Python libraries like NumPy, in a production environment, the underlying geometry behaves exactly the same. Both approaches will smoothly output that highly similar 0.974 score we saw earlier.
Finally, Section 6, Summary, connecting the math, bringing it all together.
Let's wrap up by bringing all of these chalkboard concepts into focus. We discovered that raw distance completely tricks us, and that isolating the directional angle is the key to solving the magnitude trap. By taking the dot product and dividing it by the norms, we extract a brilliantly clean, bounded score from -1 to +1. This single, incredibly elegant equation truly is the beating heart of modern semantic search and AI embedding technology.
So now that we've mastered comparing just 2 vectors, it leaves us with a fascinating final question for our next explainer. How on earth do neural networks efficiently process and transform millions of these arrows simultaneously without grinding completely to a halt? Well, the answer is matrix multiplication, and understanding it unlocks a whole new level of AI capability. Until next time, keep exploring the math behind the magic.